thank you very much, Germán. I pass the word to you.
Thank you, Leonel. Thank you for the invitation. I barely recognize myself with the presentation. I want to say good morning to all people and good early morning to Enrico and good early morning today. I will turn off camera because my connection is not very good.
Perfect.
In this presentation, we will focus in a critical participant in our experience, which we usually forget and we need. I'm going to introduce, as Leonel told you, a new fluorescent proof, and I want to show the rationale or logic behind its design. We tried to shift the spectral absorption employing an anthracene moiety compared with the naphthalene moiety of Laurdan. We claim we are making an analog to Laurdan and made the comparisons corresponding, keeping or trying to keep the electron donor and acceptor groups as a key point of the photophysical behavior of the proof. At this point, I have to mention Vicente. He was the synthetic organic chemistry who prepared the proof, and he never saw the result. Sorry, he passed away before the publication of our work. It's not advancing. Well, I want to start with the definition of Weber about of a solvatochromic proof or fluorescent solvatochromic proof. He claims that they have two functional groups with an electronic acceptor and donor character linked through an aromatic ring. And he claims that these effects will be greater if you separate more these groups. I don't know if Weber really state this definition, but I usually mention his definition. Dave can tell us if this is true. Yeah, but it's a clear, simple, and direct definition where the term generally is used because some solvatochromic proofs like pyrene involves transitions which are blocked by the presence of the solvent and no charge separation is involved. Of course, behind this definition there are several additional properties that we normally overcome or usually simply skip. We need, of course, is a fluorescent proof, high emission quantum yields, but we used to overcome the problem with more proof, more power, and the problems associated to these solutions. The second problem is photochemical stability. Of course, we need the proof be there during all our experience. In the case of Laurdan, for example, we solved this issue, the bleaching of Laurdan, moving to photon excitation. So we can solve some of the problems. And subsequent condition which we think we usually forget is the topology of the proof. We need to sense a system, and if we disturb the system, we are measuring the system and proof. So we need proofs of similar topology. And the other point is that the proof, our molecule, has to be located where we want to make the sensing, where we want to sense. Okay? During the last years, several authors have proposed homologues of DAN proofs. I think homologue is a hard word. I think that they at least accomplished the general definition of Weber, but they are not, for me, homologues. I don't want to enter in any controversy. Among them, there are fluorine. They change the aromatic rings by a fluorine or with a pyrene derivative. These proofs effectively show large shifts in its emission when they are tested. I put several examples with a reference if you want to see. They are probably better emitters than Laurdan, but we will talk a little about. Here there is one with pyrene. And even they say that they are redesigning Laurdan proof. And they are not using precisely Laurdan in this proof. I have to say that we must accept that Laurdan is Laurdan, yeah? Okay, and it's not only its photochemical behavior which makes it one of the most employed fluorescent proofs. Prodan has the same fluorophore and probably involves the same or similar excited states, but is not the same than Laurdan. Location is critical. And Laurdan has the perfect balance, hydrophilic lipophilic balance, which allows it to locate precisely in a, of course, I'm talking in a membrane, in a phospholipid bilayer. Probably all these proofs are comparable and homologues in homogeneous media. Yeah. I said Laurdan locates in a precise place where it can sense water penetration adequately and suffer dipolar relaxation and give the response we use. We change it or switch it to a anthracene group. And in order to try to locate the proof in the same place of Laurdan, we remove several methylene units. I have to say here that we made, or more precisely, I made a mistake. When I talked with Vicente, I asked for 8 methylene units, and immediately I put the name according Weber's notation, acronyms, CAPRYDAA from caprylic acid. The amino anthracene is the meaning of this name, but if you make a count, you have 9. And I discovered the extra methylene, very advanced investigation with the name defined, etc. So we keep the name, but the compound is not a caprylic derivative. Even worse, it has 9 methylene units, and there is no common name for non-natural acids of this kind. And well, we made a second mistake, but I will talk you. No, it's not going in the right direction. Well, we achieved effectively a movement of the absorption, and according to Weber's definition, we have the donor and acceptor groups separated, and we expected a higher dipolar moment in the excited state. To test this, we made Lipper-Mataga plots where the Stokes shift, the difference in the bands of absorption and fluorescence and emission, plotted against a parameter of the solvents, which involves dipolar constant and refractive index allows a linear response from where we can know the difference, the change between the dipolar moment of the excited state and the ground state. If you can see the plots for Lordan and CAPRYDAA are almost the same. We have even a lower slope for CAPRYDAA, but we have to remember that in this model is considered the volume of the proof. So probably consider a higher volume for CAPRYDAA. This difference is in the order or little higher. Well, so we kept the dipolar moment in our proof. As I told you, we made a hypothesis that the position of CAPRYDAA will be the same and the penetration of water to relax the excited state will rise similar results, but according to our results, the sensitivity of CAPRYDAA to dipolar relaxation is less than Lordan. So probably we missed by 1 or 2 or probably more methylene units, and we have to make a cut here in order to move the proof to the interface. Well, as Leonel has said, Luis told about this a little, we propose 2 extreme excited states, one locally excited state and one relaxed state where emissions come from. Upon excitation, the water dipoles, solvent dipoles are bad oriented, and if they are there and can reorient, the level is stabilized and the emission moves to lower energy or higher wavelengths. So assuming the same model for CAPRYDAA that is used for Lordan, we know that the model is more complex. Usually, and depending on the wavelength of excitation, we saw more than one excited state here. Plotting in the first phasor space, in the Fourier space, the phasor plots, when the decay of this excited state is more exponential, we can simply saw the point on the universal circle. When they are involved more complex the decay kinetics, the point you see is inside the circle. But these states are present in the same moment of excitation. The relaxed state is generated after some time after the pulse, and the phasor plot or the plot in the phasor plots appear outside the universal circle. So in an easy way and with a simple inspection in the Fourier space, you can understand what's going on. More exponential, complex model, or even excited state reactions. In the case of working in the time space, you have more difficulties to analyze the system, and usually you need a mathematical model to understand what's going on. So it's clear that phasor plot is a free model option to analyze what's going on. I have to say that these decays are not of CAPRYDAA, are simple examples of the processes involved. Well, for the chemistry of Lordan and supposing CAPRYDAA similar is not fully understood. And even more, several authors are now involving the presence of rotamers. They have made calculations and they propose that there are two different rotamers involved, and depending on the fluidity of the media, the possibility of one rotamer or the other or both change. This, of course, if it's true, includes a further complication in the models. I think they used data of Luis Bagatoli to make this sort of fitting. I didn't put the reference, sorry. Well, let's start with Caprira characterization. As I told you, the absorption spectra moves to the red and emission too. We have the possibility of excitation at longer wavelengths than Lordan, and emission también also is shifted. If we make the representation of the spectra in the spectral phasor plot, we can see the same behavior for CAPRYDAA and Lordan. I have to remember you, probably Leo told you that we cannot compare directly spectral phasor plots when the ranges are different. We only can say, yes, the maximum is moving in the same direction and the signal is broadening when we change in this series of solvents. The second point our second point of interest was to see if we can excite CAPRYDAA with 2 photons. Also with 1 photon. Here you have the absorption spectra in dimethyl sulfoxide in the black line. The blue dots are Lordan with biphotonic excitation, and CAPRYDAA in red with 2 photon excitation. So we can excite CAPRYDAA with 1 photon in around 480-84, and with 2 photons in 900 nanometers. Well, we made several tests in different media. We made multilamellar vesicles of different composition in order to have differently ordered media for our proof. You can see that response of CAPRYDAA and Lordan are similar. We have different response. I forget to say you that channel 1 corresponds to blue channel where polarity is sensed, and channel 2 corresponding to green 1 correspond to or senses dipolar relaxation. So let's start with Lordan. In channel 1, decays are clearly mono-exponential, lying on the universal circle, and channel 2 shows clearly that dipolar relaxation is operating and signal moves out of the universal circle. In the case of CAPRYDAA, we have good signal in both methodologies, but we can see that channel 1 shows the points inside the universal circle, indicating that there's a more complex kinetic or photochemical scheme operating. Channel 2 shows effectively a movement outside of the circle, and dipolar relaxation. This effect is more clearly seen in two-photon or for two-photon excitation. So here we have the possibility of overcome a drawback of Laurdan is that we can excite with one photon system. Well, here we have the results numerically. The same results you observe in the phasor plots can be given in a table with modulation and phase lifetime. For Laurdan, you can see that both times are almost the same, so we are on the universal circle. In the case of dipolar relaxation, the modulation time is shorter, indicating an excited state reaction. In the case of CAPRYDAA, as I told you, we move inside the circle with modulation lifetimes longer than the phase lifetime. This means probably B exponential decay or the participation or more than one state or segregation of other type. In the channel 2, dipolar relaxation, we have the same effect observed for Laurdan. Different times, but shorter for modulation ones. Also, we made or try to make hyperspectral analysis. Here I'm showing you a spectral phasor plot obtained in the same multilamellar vesicles I showed before. The separation of the emission is worse than for Laurdan. I insist that this kind of phasor plot is better not to be compared, but it's clear that we have more room here for analysis than here. But anyway, we are sensing the lipid order with this proof. Additionally, in order to analyze spatial resolution, we work in UVs of different composition, generating different domains, and we can see that we are able to segregate spatially the situation or the observation of our proof. Finally, we made the same analysis in live cells, or equivalent analysis in live cells, and using different masks, you can see the behavior of the proof in live cells. So yesterday, someone said me that live cells are not in vivo. I don't know if it is correct. Well, in order to end and conclude the presentation, the CAPRYDAA proof, fluorescent proof, behaves in a similar fashion to Laurdan, but of course is redshifted, which makes easier the excitation with single photon methods. Of course, in the case of Laurdan, we cannot use single photon method because bleaching. The proof shows to be excitable with two photon, which also allows the its use combined with other fluorophores, which absorbs in other regions. It shows to be sensitive to dipolar relaxation. I told you that it's less sensitive than Laurdan, but we think we can modulate the position of the proof and obtain a better sensitivity to this property. As I show you, can be used to make a study, a spectral or lifetime study, and there is a correlation between both, allowing hyperspectral analysis. And also, the last slide I show you it's possible to use this proof in live cells and use the models we use. Well, thank you for your attention, and thank you, Leonel.
Thank you very much, Germán. Very nice talk. This is a wonderful proof that we have been working on, and I think we have much more to do with the proof and the new designs that we want to do too. So we will have time for one question. Felipe raised hand, so I think we are enabled.
I already asked a question, so I'm gonna
Okay.
send my
Okay,
space
perfect.
to Nadia.
Okay, perfect. I will read Nadia's question. Thank you, Felipe. I have a naive question. Have you seen any effect in cardiolipin-rich lipid mixtures?
No, we made the work in order to make a comparison with Lordan. So till this moment, we have only tested, what can I say, normal lipid mixtures. We have to advance in the direction of course, we can give who is interested proof to make the proofs they want to do. So only with the COVID situation, we have run it out of CAPRYDAA, and we have to synthesize more. But we are happy to borrow or to give some sample who needs.
Okay, thank you.